All right, this is a very, very long example, but is also very, very important. It basically discusses most of what we've already talked about. So we'll do it together, but you better make sure you can do it by yourself. All righty, so here we have a graph. This is, notice what it says. It says the displacement of x at one particular time. And it's in millimeters, I don't care, whatever. And notice this is x. Okay, so there's no time, and it says right here, right? This is what it looks like at time equals 0. So this is what they call a snapshot graph, right? It's like a, you know, if I made a rope wave and we just took a picture of it. So we see what that rope wave looks like at one particular time. So it's a snapshot. Okay, so number one, find the wavelength and the period. Okay, this is x. So I can find the wavelength. So what's the wavelength? I'm going to do it right this time. So you start here and you go, whoop. So what's the wavelength? 2 meters. So number one, wavelength is 2 meters. Just get it from the graph. It's great. Now, the period. Is there any way to get the period from this graph? Of course not. There's no time variable. So what do? Use F equals ma. Right? F equals ma. F equals ma, you know, for a wave. Okay, so V equals F lambda. Now, we want to get the period. Well, remember, F is 1 over the period. So we get lambda over the period. Yeah? Remember. I mean, you got to remember all these things. Sorry. F is 1 over the period. And omega is 2 pi f. Sorry. You just got to know them. Okay. So therefore, since this is true, solve for the period. So the period is the lambda over v. Well, lambda is 2 meters. Velocity they give us, 200 meters per second. So that's a 0.01. All right. Okay. There you go. Units are correct, right? The period is the time for one wavelength, you know, to move one wavelength. So it's in seconds. Awesome. 2, we want to draw graphs at time equals 1/4 of a period and time equals 1/2 of a period. Oh, golly. So I'm going to do it 2 ways, the easy way and a hard way. We'll do the easy way first. Now, what is this? Is this a sine or a cosine? Well, it's a cosine, right? It's a nice cosine. And we know that cosine is periodic in the wavelength, lambda, and in period t, uppercase T. So when the thing moves 1/4 of a period, how much of a wavelength has it moved? 1/4 of a wavelength. When it's moved 1/2 a period, it's moved 1/2 a wavelength. That's all. You know, whoopee. And it's moving to the right. Okay? So for number 2, we'll do time equals 1/4 of a period first. Because I have to draw this. Oh, golly. Okay, so basically, again, we're going to shift this. We're going to shift this thing 1/4 of a wavelength. 1/4 of a wavelength. And here is 1 wavelength. Right? So the wavelength is 2. So we're going to shift it 1/4 of that. What's 1/4 of that? 1/2. Right? So we're going to shift it. So we're going to shift it 1/2 a wavelength. Oh, gosh. So I got to draw that. Okay, so again, so 1 period corresponds to 1 wavelength. So 1/4 of a period corresponds to 1/4 of a wavelength. Yeah? Okay, and the wavelength is 2 meters. So 2 meters over 4 is 1/2 a meter. Yeah? Okay, so let's see. So we just have to shift this thing 1/2 a meter. All right? So this is 1/2 a meter. So this is going to be up here. This is going to be here. So I'm just going to have to draw this. Just bite the bullet and draw it. Okay, so I'm just going to be like, so 1/2 a meter. So, okay, so this is going to be here. Right? And then this is going to be, okay, so this is going to be there. So, you know, it's like that. Right? Yeah. Okay? Everybody agree? I just shifted this thing a half a meter. All right, let's do the next one. Where'd it go? Okay, the next one is the time is a half a period. And same thing, right? The period is a wavelength, so half a period is a half a wavelength. So a half a period corresponds to a half a wavelength, which is 2 meters over 2, which is 1 meter. So I'm shifting this thing by a meter. So this is going to go from 0 to 1. It's going to go from 1 to 2. Just shift it, you know? So let's see if I can do that. Okay, so this gets over here, right? And then now this, okay, this is 1, so this is going to be -1, right down there. So it's kind of like, let's see, oh, sorry. So, and 2, like that. Right? You do it right? This is going to be at 3. Yep, I did it right. Yay! All right, any questions? So I think this is the easiest way, you know. Just remember this part. And then just go there and go there. Okay, that's one way to do it. Let's do it a different way. Harder. More complicated. But it's all right. It's not that bad. Okay. Number 2. Okay, distance equals speed times time. No kidding. Now, the delta t is, for the first part, is a fourth of a period. Now, we know that the period is 0.01 seconds, so we want a fourth of that. So it's 0.0025 seconds. Okay? So, plug it in. So delta x is velocity, 200 meters per second, times delta t, 0.0025 seconds. I promise you, you work that out, you get half a meter. Well, gee, isn't that what we had the last time? Yeah, but this is just a longer, just another way to do it, right? So we just shifted a half a meter, right? That's what we did the last time. Okay, let's do the other one. So now we want delta t to be a half a period. Well, that's 0.01 seconds over 2. So that's 0.005 seconds, right? And then delta x is v delta t, 200 meters per second, 0.005 seconds, and you get 1 meter to the right. So, I mean, you get the same thing as we had the last time. So just shift the whole thing to the right. So, you know, you pick what you like, right? Do the first, you know, this may or deal with it, whatever, it doesn't matter. Okay, so we've done 1 and 2. Just in case I need it, I don't know if I'm gonna. Okay, number 3. Ugh. Draw a graph if the wavelength is halved. I don't like drawing. Whatever. 1, 2, 3. Okay, so now the wavelength is halved. Okay, so what does that mean? So this used to go from 0 to 2. Now we want to scrunch it, right? Wavelength is halved, so that means it's going to be at 1. Okay, so just draw it. Right? So this is going to be at a half. So, whatever. Something like that. Okay? All right. Okay. Number 4. Everybody agree? Just. Okay, number 4. Draw the graph. If the frequency is halved, the speed is unchanged. Okay, so for number 4, so the frequency goes to f over 2, but v is constant. Okay, so what equation did you use? What equation you always use? When in doubt with waves, use f equals ma, where this is what I call f equals ma, right? Okay, so this becomes f over 2. This remains the same. So what has to happen to that? It has to go to 2 lambda, right? It has to, you know? Okay, so all right, so for number 3, we do the graph if the wavelength was halved. For number 4, we have to draw the graph if the wavelength is doubled. Okay, so that means that this is going to go to 2, this is going to go to 4, and da-da-da-da-da. All right, so here you go. Okay, so we start out here. Okay, this used to be, let's see, this used to be at 1/2, it's going to be at 1. And then this used to be at 1, so it's going to be at 2. This used to be at 1.5, it's going to be at 3. Oh, so it's going to be this, right? Yeah. Okay, any questions? You can't ask questions, sorry. Too bad. Just kidding. All right. All right, let's see. Number 5. Okay, number 5 says the phase constant is increased by pi. Okay, so it says the phase constant is increased by pi. All right. Now, go back to your parabola. You know, y equals x plus, okay, sorry. Y equals x squared looks like this. Y equals x plus 1. What does that look like? Like that, right? If you have a plus, it moves to the left. Okay? So, now, what if this were 2 pi? Well, you know, sine is periodic in 2 pi, right? So if this were 2 pi, it would look exactly the same, right? It would look exactly the same. So in other words, 2 pi corresponds to a wavelength, right? So what does pi correspond to? Wavelength over 2, right? So all we have to do then, okay, and again, wavelength is 2 meters. This is 2 meters divided by 2, that's 1 meter. And it's a plus, so it goes to the left. So all we have to do is shift it 1 meter to the left. So we're going to shift it 1 meter to the left. Okay, so this is going to go here. 1.5 becomes 1/2. Okay, 2 becomes 1. Anyway, and so forth. Yeah. Okay? All right, so we just shifted it 1 meter to the left. Okay, number 6. Number 6. Draw the graph if the tension, so this is a string, I guess, right? Because, you know, it's tension string. So the tension is decreased by a factor of 4. The frequency is unchanged. Okay, wow. Well, come on, as soon as you see that word tension and it's a string, you know, what you better think of is this. It's the only thing that we know that has tension. By the way, they put this little s here just to remind us that it's a string. So this is the tension of the string. Okay? All right. So the linear mass density doesn't change, but this gets smaller by a factor of 4. So this becomes this, right? Because it became smaller by a factor of 4. But then that is the same thing as this. All right? So therefore, what's that? So the velocity is decreased by a factor of 2. Okay? Now, don't forget, F equals ma. Okay, so this has become v over 2. The frequency is constant. And so what happens, so I'll just say constant. And so what, look at it, if this has got factor 2 smaller, this remains the same. This has to be lambda over 2 as well, right? And so isn't that just what we did for number 3? All right? So the answer to number 6 is the same as the answer to number 3. Psh, goodbye. All right? So the wavelength is halved, that's all. Okay, so we use a lot of relationships in this example, you know, so make sure you go through it on your own. Make sure you understand them, because this is really this is just the basics, right? Okay, very good. All right, ugh, there's that crummy color again. Oh, whatever. Okay, there are actually 2 speeds that we need to be concerned with a transverse wave. Well, with any kind of wave, actually. So we already learned about this, right? This is the wave speed. This is how fast that pulse, just consider a transverse wave. This is how fast that pulse goes, right? The pulse goes to the right. And of course, we had a different formula. This is just for the string, you know. Now, but wait a minute. You know, here's a transverse wave, right? And the pulse is moving to the right. But what did we learn? So here's, let's say that's the spot that I sprayed with my can of spray paint. What is this thing doing? It's going up and down. Okay, so we call the speed of the wave, or the wave pulses, whatever you want to call it, v. Now, this is just a piece of the rope, right? This is the disturbance, you know? This is the piece of the rope. And it's going in the y direction. Hey, let's call it Vy. Right, so we're going to call it Vy. Okay? So there's 2 speeds you have to worry about. So this is called the transverse speed. Right, that Vy. And you know, what's Vy? Vy is just dy dt, you know? Now what do you mean y? What's y? Okay, so this is what I'm sorry, I kind of did a trick on you. All right, so now I decided to call the displacement y. Why did I do that? Well, no good reason. Well, because if I'd have written this, it would look stupid, right? Yeah? That looks stupid, don't you think? dd over dt, it looks stupid, right? So I don't want to do that. So instead of using d for the displacement, I use y. All right? That kind of makes sense because it's moving in the y direction. So just dy dt. Okay, let's figure it out. So the displacement, x versus t, which I'm now calling y, sorry. Remember, it's a sine kx minus omega t plus phi 0. Boy, you're going to see this equation a lot. Over and over and over again, you know? Okay, so therefore, Vy, which is dy dt, okay, you got to remember your chain rule, right? Okay, so what's the derivative of, remember, it's a derivative relative to dt, right? Right? So dt. So what's the derivative of sine? Cosine, right? And then, but here you have to take, but here you use a chain rule, you get a minus omega in front of it. So you get a minus omega a cos kx minus omega t plus phi 0. So I know some people forgot how to take a derivative. You better not forget how to take derivatives, all right? Don't forget your chain rule. Okay, so there it is. All right, so that's all you had to do, right? So Vy, the transverse speed, minus omega a cos blah, blah, blah. Now, let's just kind of fool around with this for a minute. See if Mother Nature agrees with it. All right, so again, we're just looking at the transverse speed, right? A piece of the rope. A piece of the rope. Come on. There you go. Yes, yes. Okay. All right. Okay, so just like we did before, you know, we're concentrating on Vy, and we want to do a test. Does it depend on the amplitude? Does it depend on the frequency? Does it depend on the tension? Just like we did, you know, with the wave speed. All right. Okay, so here we go. So again, I would say concentrate on this. Oh, golly. All right. Okay, so we're just concentrating on the speed of this. Kind of slow, right? Kind of slow. Okay, now what we want to do, let's crank up the amplitude. So what do you notice? Faster, right? Faster. Does that make sense? Yeah, right there, right? Okay. Now we want to change the frequency. Let's change the frequency. Okay, what do you, oh gosh, forget it, I can't. It goes faster. Right? Where's that second dot? I don't know. That's crazy. Okay, now let's change, okay, so this had an effect, right? So this had an effect, which made sense because it's right there. This had an effect, which makes sense because omega, don't forget, omega is 2 pi f. Okay, now tension, should tension, this is tension, sorry. Ooh boy, that's going to kill us, huh? Sometimes we have uppercase T for period, sometimes we have uppercase T for tension. So you got to be careful because one is a force and one is a time. But you shouldn't get them confused. Now, does this depend on tension? No. So the prediction is it doesn't have any effect. But let me slow this down because I can't, it's too fast. Yeah. All right. So I'm concentrating on, it's still too fast. All right. Yeah, that's much better. So concentrate on this guy. All right. Okay, let's zip up, let's move the tension. Okay, let's make it small. Did it change this at all? No, not at all. Okay, so this has nothing to do with it. So, I mean, this is reasonable. Yeah, that's all I'm saying. Right? So it depends on, of course it depends on this, but I mean, the amplitude depends on the omega, which is the frequency, and the A, which is the amplitude. All right. Okay, this is a challenging question because you can't read it. There you go. All right, 2 strings, one thick and one thin. So what are you thinking of when you see that? I mean, where have you seen anything that has to do with thickness or thinness, you know? The only equation that has the thickness or the thinness is the velocity of the string, which is the tension over the mu, right? This is the mass per unit length. So that has to do with like if it's thin or thick or, you know, density, right? All right, so we kind of think that we're going to probably use this equation somewhere. 2 strings, one thick and the other thin, are connected to form one long string. A wave travels along the string, passes the point where the 2 strings are connected. Which of the following change at that point? So pause your video and figure it out. And of course, you're going to use this, and you're probably going to use F equals ma too. Well, we'll see. I would guess. All right. Okay. So we're assuming that the linear mass density changes. Okay. All right. So if this changes, then the velocity of the wave has to change. All right. So we're saying that this changes, and so therefore we know that v changes. All right. Now, the frequency never changes. I mean, unless you make a change. All right. But the frequency is a frequency. You'd have to change it. The source would have to change or something like that. So the frequency doesn't change. So this changes. This is constant. So if that changes, that's constant. This has to change. That's all. Okay. So the speed changes and the wavelength change. All right, let's quit. I think that's about 30 minutes.